Electricity consists of elementary phenomena: the conduction of electricity through solutions, through gases, and through vacuum. In passing a current through a solution of silver nitrate, we find that metallic silver is deposited out. Exact relationship exists between the weight of this silver and the amount of electricity used. We shall now deposit silver on a spoon, which first we have carefully weighed. Then we make the spoon the negative electrode in this solution of silver nitrate, through which an electric current is passing. We measure the current with an ammeter and the time with a clock. The amount of silver deposited during this time, represented by this additional counterweight, depends on the product of the current by the time. Just as in flowing water, the total quantity of water is the product of the rate of flow by the time of flow, so in the case of electricity, the product of current by time measures the total quantity of electricity. Next, we use acidified water. The electric current here releases oxygen and hydrogen, accumulating in the vials at the top. Using the same current as before with silver, and for the same length of time, we discover that only 1/108th as much hydrogen by weight is released as was silver. Now, an atom of hydrogen weighs about 1/108th as much as a silver atom. Therefore, the same total charge which passed through the two solutions must have released the same number of atoms of hydrogen as of silver, and we conclude that atoms of hydrogen and silver carry the same charge. If we use molten zinc chloride, however, we find that only half as many atoms are removed from the solution by the same quantity of electricity. An atom of zinc must therefore carry twice the charge of a hydrogen atom. Similarly, it has been found that atoms of all elements carry simple whole number multiples of the charge carried by hydrogen. These, among others, 1 unit charge. These, 2 unit charges, and of the common elements, only aluminum, 3. Thus, we see that electricity comes in very small packages or units, which are never subdivided. To this astonishing conclusion, we are led also by experiments on the conduction of electricity through gases. Ordinarily, gases are non-conducting. Electricity normally does not leak off charged wires in direct contact with the air. Likewise, an electroscope will hold its charge almost indefinitely. If, however, a flame is held near a wire attached to the electroscope, the leaves collapse at once. Similarly, X-rays produced even at some distance cause the charged leaves to collapse. We can explain these phenomena if we assume that the flame and the X-rays caused air molecules to become charged, some positively and some negatively. With a positively charged electroscope, negatively charged molecules are attracted to the knob and cause some of its charge to be neutralized. Furthermore, when the electroscope is negatively charged, positively charged molecules present cause the leaves to collapse. When the X-ray tube is turned off, these charged molecules called ions are no longer formed. Those remaining neutralize each other, and thus the air again becomes a non-conductor. To measure the charge of such ionized particles, oil is atomized, and the drops become charged in the process. A drop is allowed to settle between 2 charged plates. When the drop and upper plate are negative, and the lower plate is positive, the drop is pulled down by both the electric field and gravity. If the field is reversed, the drop will be forced upward by the electric field against the pull of gravity. Therefore, the difference between downward and upward speeds permits accurate measurement of the charge on the oil drop. The charge on the drop may be changed by ionizing the air with X-rays. If a positive ion collides with a negative drop, the charge on the drop is reduced. The change in charge can be measured by the change in speed. Never during thousands of observations has a charge been discovered which is less than the unit charge on a hydrogen atom found by electrolysis. Oil drops always have exactly this amount of charge, or a whole number of such charges. As to the charges themselves, it is only in vacuum that we can detach them from matter and observe effects due to them alone. This evacuated bulb contains a glowing filament and also an additional electrode. When this electrode is kept positive, a current is registered by the ammeter. No charges flow if it is negative. The evacuation of the tube has largely eliminated any gaseous ions which, if positive, could move from the electrode to the filament. Therefore, we must assume that negative charges from the hot filament have traveled to the positive electrode plate. This current can be carried for a considerable distance through vacuum. As we cease heating the filament, the flow of charges stops. This is the principle of vacuum tubes used in radios, phonographs, public address systems, and talking pictures. To render the path of these charges visible, we have placed a screen of zinc sulfide inside the tube, eliminating all but a narrow beam of charges by means of a slit. When the charges strike the screen, their path is rendered luminous. If a magnet is brought near, the path of the charges is deflected, just as a current in a wire would be. Here we have the current, but no wire, and since the tube is highly evacuated, there are no ion carriers either. Let us assume that each individual charge in this moving stream is the elementary unit charge of electricity determined in the oil drop experiment. These unit charges, which we call electrons, can even be swung around in circles by a suitable magnetic field. This offers a method of determining their mass. Just as it is possible to determine the mass of a stone at the end of a swinging rope, if we know the length of the rope, the speed of the stone, and the force the stone exerts upon the rope, so is it possible to determine the mass of these electrons. This mass has found to be 1/1845 of the mass of a hydrogen atom. A very convenient method of obtaining electron streams is to place a metal within an evacuated tube and then permit X-rays to shine upon it. This radiation releases electrons from the metal. The remaining positive charge soon prevents any more electrons from escaping. If, however, we insert another electrode kept positive with respect to this piece of metal, a continuous flow of charges is produced, which may be registered as current by a galvanometer. This electron stream has the same properties as that obtained from hot filaments. This phenomenon is used in the photoelectric cell. Such cells are adapted for soundtrack on film by using ordinary light with the more active metals like potassium or cesium. The varying opaqueness of the soundtrack changes the amount of light reaching the photoelectric cell in the projector. The cell, therefore, delivers a varying current, which is amplified by vacuum tubes and then translated into sound. Of the utmost importance to modern science was the astonishing discovery that, whatever the origin of the electrons, hot filaments of tungsten, or X-rays on zinc, or led to the discovery of the electrons, elementary units of electric charge. These electrons constitute the fundamental building blocks of the atoms and molecules of matter in its infinite variety of forms.